Question number 4 is an equilibrium question where calcium carbonate is decomposing into calcium oxide and carbon dioxide. And the question says, when heated, calcium carbonate decomposes according to the equation above. A student adds a 50-gram sample of the calcium carbonate to a 1-liter rigid container. They pump out all the gas, and then they heat it up to 1100 Kelvin. As the container is heated, the pressure is measured over time. It's plotted in the graph below. The student repeats the experiment, but then uses 100 grams. So the first time they used 50, this time they used 100. In the experiment, the final pressure is 1.04, which was the same final pressure as in the first experiment. So this graph here is from the first experiment. It's also the graph for the second experiment as well. In this case, that line right here represents 1.04 atmospheres. So part A says calculate the number of moles of CO2 gas present in the container after 20 minutes of heating. Well, we know at 20 minutes here we are clearly at equilibrium. That pressure is not going to change. It's 1.04 atmospheres. So we know that N equals PV over RT, and the pressure is 1.04 ATM. The volume, let's go back up, is a 1-liter container over the R value, 0.08206, times the temperature, which is 1100 Kelvin. Yes, 1100 Kelvin. Okay, and now we're going to take those numbers, we're going to multiply the numbers on the top, divide the numbers on the bottom, and we get a pressure, or excuse me, not a pressure, a number of moles equal to 0.012 moles. And that is just a 1-point response for the correct answer. Okay, part B says a student claimed that the final pressure in the container in each experiment became constant because all the calcium carbonate had decomposed. Based on the data, not based on anything else, you have to base it on the data in this experiment. Do you agree with this claim? No, I do not agree with this claim. You can't say because it's an equilibrium reaction. That's not data. That's a good way to answer that question, but unfortunately that's not based on data. The data is we started with 50 grams and then we started with 100 grams, and in both cases we got to 1.04 atmospheres. So based on the data in this experiment, do you agree with this claim? No, because, and again, I'm not going to write it all out, but because whether you start with 50 grams or 100 grams, we still get to a constant pressure of 1.04 atmospheres, which means that there's still some of the reactant left over. So some of that calcium carbonate does not decompose. If we had gotten different amounts or different pressures of CO2, then we could say yes, all of the CaCO3 got used up when we only had 50 grams. But since we got 1.04 atmospheres, we get to this pressure in both cases, then we know that there still has to be some calcium carbonate left over. Okay, also a 1-point response. Okay, after 20 minutes, some CO2 is injected into the container, initially raising the pressure to 1.5 atmospheres. So would the final pressure inside the container be less than, greater than, or equal to 1.04 atmospheres? So again, the final pressure inside the container. So this is one of those cases where you're at equilibrium. We're basically starting with that same graph from above. So we're at 1.04, and then all of a sudden it jumps up to 1.5, it says. And then we know when that happens, it's going to cause a shift back to the left. So the amount of CO2 is going to start to go down. Now, typically, it doesn't go all the way back down to 1.04. But in this case, this one's a little bit tricky because we know that the Kp or the Kc value is simply based on the pressure or the concentration of CO2. And we know that the equilibrium constant value cannot change unless the temperature changes, which means if Kp is based on the pressure of CO2 and at equilibrium the pressure of CO2 is 1.04, that means that number can't change. So this value, this pressure here, has to drop all the way back down to 1.04 so that that equation there can remain true. Okay, so would the final pressure inside the container be less than, greater than, or equal to? It will be equal to. And then to explain your reasoning, you simply say because Kp equals the pressure of CO2, that the Kp value can't change because the temperature change did not happen. Okay, also 1 point. And then question D, are there sufficient data obtained in the experiments to determine the value of Kp? Justify your answer. It doesn't say to calculate it, but it says, is there enough information? Well, remember in part C, we just said Kp equals the pressure of CO2. So, do we know the pressure of CO2? Yes, we do. If we know that, then we know the Kp value. So, is there enough data? Yes, there is. And justify your answer because Kp equals the pressure of CO2, and we know the pressure of CO2, so we can find that value. Okay, so 1 point there. That is a 4-point response. Give yourself a score out of 4. Okay, question number 5. Some binary compounds that form between fluorine and various nonmetals are listed above. A student examines the table and poses the following hypothesis. The number of fluorine atoms that will bond to a nonmetal is always equal to 8 minus the number of valence electrons in that nonmetal atom. So based on the student's hypothesis, what should be the formula of the compound that forms between chlorine and fluorine? Well, the hypothesis is that the nonmetal is 8 minus the number of valence electrons. Well, chlorine has 7 valence electrons. So 8 minus 7 is 1. So the number of fluorine atoms that will bond to chlorine is 8 minus 7, which is 1. So what will be the compound that forms? It'll be ClF or FCl, whichever way you want to write that. Okay? And that's a 1 point response. And it has to be just straight ClF. Okay, letter B is asking you to draw the Lewis electron dot diagram for ClF3. So the first thing, 28 valence electrons. I'm going to put the chlorine in the middle. I'm going to put the 3 fluorines around it. I'm going to complete the octet with 6 more electrons around each fluorine. And that adds up to 24 electrons. So I have 4 left over. So 25, 26, 27, 28. So you need to have 3 single bonds and then 2 lone pairs on that central chlorine atom. That is also a 1 point response. Okay, part C says 2 possible geometric shapes for the ClF3 molecule are trigonal planar and T-shaped. And hopefully right away you look at that and go, well, duh, that's not trigonal planar. Trigonal planar is 3 bonds, no lone pairs, and therefore it must be T-shaped. But again, just kind of go with the question. The student does some research, learns it does have a dipole moment. Of course it has a dipole moment. It's got that lone pair. It's asymmetrical. The dipoles don't cancel. Okay, which of the 2 shapes is consistent with the fact the ClF3 molecule has a dipole moment? Obviously, you're going to say T-shaped. Okay, and then you would say that it's T-shaped because the lone pairs of electrons on the chlorine atom, again, does not allow the bond dipoles to cancel. So there I am talking about bond polarity. So I talked about the lone pairs of electrons on the chlorine. So there I'm mentioning the molecular structure. And then I say the bond dipoles don't cancel. And that also, again, I'm talking about the bond polarity there. Notice that when they say justify your answer in terms of these things, make sure you talk about those things in your answer. Okay? And that also is simply a 1 point response for saying T-shaped and for having the correct explanation. Okay, and then the last one here, this is a tricky one. I don't like these. So the student does some more research. They find that there's also these compounds here. We know that 2 of the compounds that we've talked about are ClF, and then they talk about ClF3, which they don't include there, but that you certainly could. So it says, propose a modification to the student's previous hypothesis to account for these other compounds. So it's not just 8 minus the number of valence electrons. How can you modify that hypothesis to now include all of this here as well? So there's a couple of different answers that they accepted here. One of them is, you'll notice that every single one of them simply has an odd number of fluorine atoms. So if you change it to simply include odd number of fluorine atoms, that's one answer that they accepted. They also accepted, notice that as you go from fluorine to chlorine to bromine to iodine, that the number of compounds increases. So you could say as the atomic number increases, the number of fluorine atoms also increases. Okay, and those are really the only two answers that they accepted. Again, those are tricky questions, but that was a 1 point response. So there's our 4 points for question number 5. Question number 6 talks about polypropylene versus PVC, like a PVC pipe. Okay, question A says, given that the spacing between polymer change and polypropylene and PVC is similar, the beads that sink are made of which polymers? So when things sink, we know that density equals mass over volume. And if something has a density greater than water does, then it will sink. If something is less dense than water, then it will float. So really what this question is saying is, which of these two compounds is more dense? And again, density is a measure of mass and volume. And in terms of spacing, they all have very similar spacing. But notice that chlorine is a much heavier atom than that CH3. That's the real difference between polypropylene and PVC, is that chlorine atom. Okay, and that since that's heavier, that means this molecule here is going to be more dense, and that's the one that's going to sink. Okay, so the beads that sink are made of which polymer? PVC. And why? Because PVC is more dense than PP because of that chlorine atom. Okay, and that is I'm just checking here, that's a 1 point response. Okay, part B, account for the boiling point differences between propene and this new one, vinyl chloride. Okay, so first of all, we should look at this and go, yes, they are both slightly polar, but this one has 1, 2, 3 carbons. This has 2 carbons and a chlorine. That chlorine throws off the symmetry more than the CH3 does. Okay, so this one is slightly more polar, and this one's going to have a larger electron cloud because, again, chlorine has a lot more electrons than CH3 does. And so in terms of dipole-dipole forces, this one's going to have stronger dipole-dipole forces because it's more polar, because of that asymmetrical, the bond dipole here is much stronger than the dipole you would have in this one. So this one is more polar, so it has stronger dipole-dipole forces. It also has a larger electron cloud around the chlorine, so the London dispersion forces are stronger as well. Now, you did not have to mention both of those. You had to mention one or the other. If you say, again, the dipole-dipole forces are stronger in vinyl chloride because it's a more polar molecule because of the chlorine atom, you get 1 point for that. Or, not and, or you get 1 point for saying that the London dispersion forces in vinyl chloride will be stronger because it's a more polarizable molecule due to the larger electron cloud around the chlorine atom. So that was also just a 1 point response. Okay, and then part C is talking about the difference between the enthalpy of combustion of this compound and the enthalpy of combustion of this compound here. So when they give you enthalpies of formation, you remember that the enthalpy change for the reaction is equal to the enthalpy of formation of the products minus the enthalpy of formation of the reactants. So we're going to plug those numbers into the equation. So the enthalpy change for the reaction is going to equal the products. So our products are CO2 and H2O. So there are 6 CO2 molecules. So 6 times negative 394 plus 6 waters. So 6 times negative 242. And those are our products. So enthalpy of formation of the products minus the enthalpy of formation of the reactants. C3H6 has an enthalpy of formation of 21. So we're going to go 2 times 21. And then oxygen is in its elemental state. So it has an enthalpy of formation of 0. So that's it. So then we plug those numbers into our calculator. Hopefully you've already done this. and you should get an enthalpy change of negative 3,858 kilojoules per mole. And now we're simply going to compare that number to this number up here. Remember, the question says, determine whether the combustion of 2 moles of propene, which is this one here, this is the one we just calculated, that's the propene value, releases more or less or the same amount of energy than vinyl chloride. So here's our vinyl chloride again. It only released 2,300 kilojoules of heat per mole. The propene releases 3,858 kilojoules per mole. So it certainly releases more. Okay, and that was a 2-point response. 1 point for saying more, and then another point for having the correct answer. Okay, and so there are your 4 points. Part C there is the 2-point answer. Okay, and then the last one, question number 7, the half-life of the catalyzed isomerization of cis-2-butene gas. Again, you don't need to know what that means. Here's the reaction right here. That's all we need to know. Okay, to produce this trans-2-butene gas, that's some organic stuff there that you will learn in organic chemistry, was measured under various conditions shown in the table below. So, notice that in trial 1 and trial 2, you're starting with different amounts or different pressures of this original compound. But notice that in both cases, the half-life is the same. Okay, and not anytime, but almost anytime they say, hey, how do you know this reaction is first order, is you look and see, is the half-life constant? They might actually give you the half-life, which makes it super duper easy, until you look down here and go, wait a minute, the half-life change. Remember, the half-life changes when temperature changes. So when everything else stays the same, when the initial pressures are different, but everything else remains constant, then the half-life will remain constant. That is an indication of a first order reaction. So explain how the data is consistent. I would just say in trials 1 and 2, at different pressures, there is a constant half-life, and that is a 1-point response. Okay, part B says calculate the rate constant for the reaction at 350. So don't use this information down here. Use the 350 ones. Okay, and so we know that half-life is equal to 0.693 over K, which also means if they're asking for the rate constant K, K is going to equal 0.693 over the half-life. And if the half-life is 100, then we're just going to take 0.693, we're going to divide by 100, and we're going to get 0.00693. Okay, and it says include appropriate units with your answer. Well, this was seconds, and now we have seconds on the bottom, so it's 0.00693 seconds to the minus 1. And you did have to have the correct units to receive the 1 point for that answer. Okay, obviously if you put that in scientific notation, 6.93 times 10 to the minus third, they also would have accepted that. Okay, part C says, is the initial rate of the reaction in trial 1 greater than, less than, or equal to the initial rate in trial 2? Well, what's a rate law? We know, they tell you that it's first order, so we know the rate is going to equal K times the concentration of that cis-2-butene, whatever that compound is. We'll just say X. Okay, and the concentration is moles over liters, which is also, think about moles over liters, N over V. Start with PV equals nRT. And you divide by V over here. And so N over V, which again is moles over liters, is equal to P over RT, right? If I move those two over to the other side, it's P over RT. So as the pressure goes up, what does the concentration do? Of course, the concentration goes up. So when the pressure goes up, the concentration goes up. So when the concentration goes up, what does that do to your rate? Of course, it makes your rate increase. So is the initial rate of the reaction in trial 1? So trial 1's the lower pressure, so it is going to be less than that of trial 2. And then to justify your answer, I would just say, using the rate law, when the pressure goes up, the concentration goes up, which means the rate will increase. Okay, also a 1 point response there. Okay, and then part D says the half-life of the reaction in trial 4 is less than the half-life in trial 1 or 2 or 3. Okay, why? Okay, and then again, it says explain in terms of activation energy. Okay, all you have to say is that at a higher temperature, more molecules have enough energy to, you already know what I'm going to say next, overcome the activation energy barrier. And so if more molecules have enough energy to do that, the reaction is going to go faster, which means the half-life is going to decrease. Okay, so it's all about at a higher temperature, more molecules have enough energy to overcome the activation energy barrier. That's a 1-point response. So there's your 4 points for that. Okay, so overall, you have those 50 points from the multiple choice. So get your score from the multiple choice. From this one, again, there are 46 points total. And we're going to take those 46, and remember, you're going to have a score out of 46. You want your score out of 50. Okay, so whatever your score is, put that here. Basically, I think I'm trying to remember what that. I think it's like 1.083 is what you multiply by. So add up your free response score, multiply it by 1.083, and that will get your score out of 50 for the free response, and then you're going to get a score out of 100. Once you have that score, again, don't worry about what the number is. Now let's just look at the scale, because really that's what matters. Is they look at it and go, okay, how hard was this test? According to the scores, this is a pretty hard test, because if you got anywhere from 72 up to 100, you got a 5. That's a pretty low value for a 5. Okay, and 4s went from 58 to 71. And then the 3 went all the way down to 42. So 42 to 57 was a 3. And if you got less than 42, does it matter if it's a 2 or a 1? Not really. So if you got less than 42, you're in the 2. I didn't write it down, but I would imagine that the 2 probably went from probably 28 to 41, probably somewhere around there is the 2 range. Okay, so hopefully you're in one of those higher ranges. And if not, remember, guys, we're still learning from this. So take this as a learning opportunity. Everything that you got wrong, hopefully you learned something from, and you're going to do better on the next one.